have let's say, two-dimensional space, for example, and you can, let's say, average this operator over with some weight function f over a small region of Minkowski space. Okay? So you can define this type of local operators. They are local in the sense that they are localized in space. They are not an integral over all of space, but an integral over a small finite region of space. And these are good operators in the quantum field theory, and they are the operators we normally talk about. Of course, an idealization of this would be to take f to be a delta function, and then we have the operator inserted at the point. But that, strictly speaking, creates a non-normalizable state. So these are the operators that create good states. So now imagine that we say that we restrict the operators we consider to be operators which exist purely on the right wedge of Minkowski space. Okay. So that's more or less the same as saying that at t equal to 0, we split the wave function. We split the state into two parts, and we focus on the degrees of freedom which are on the right side. And then, just from the knowledge of these degrees of freedom, we can determine the expectation values of operators in this whole quadrant, okay, by causality and the principle of relativity. So in this situation, we can start with the vacuum state, the vacuum density matrix. So this is the Minkowski vacuum, and that's a pure state density matrix. And we can ask how it looks from the point of view of an observer here on the right side. And so for that purpose, we need to trace out, if we wish, all the degrees of freedom that live on the other side, and get a density matrix for the right side. Okay, so that comes from tracing over h left of this original density matrix. Now, in general, when you compute such density matrices for subsystems, you don't necessarily get a simple density matrix. So in a general case, you will not get a simple density matrix. But it's a special case of this problem where we take this right wedge of Minkowski space that we actually get a very simple answer for this density matrix. And this density matrix is actually equal to, or let me say proportional to e to the minus 2 pi times the boost generator. So this is an operator, which is the operator that generates boosts around this point. So it's the operator that generates this type of transformations. Okay. And so we have this simple expression. So let's, and in particular, notice that the boost generator is can be written as all other elements of the Lorentz or Poincare group in terms of the stress tensor. So we take the integral between 0 and infinity, let's say dx1. So let's say we express it as at this time of x1 t0 0 of x, right? At let's say x0 equal to 0. So x0 is the time direction, and x1 is the space direction. X plus and x minus are x0 plus minus x1. So it's a special property of this setup that the density matrix has an expression in terms of a local operator. And so in particular, if you think of B as energy, notice that it has a thermal form. So it looks like a thermal density matrix if you think of B as energy. Now, before continuing discussing this, I'd like to give a derivation of this fact. This was initially found by Bisoniano and Wichmann, and then it was rediscovered independently by Unruh, this fact here. And it's important for black holes, and and also important for other applications that I'll discuss later. But first, let's give a simple derivation of this fact. So in order to calculate this, what do we need to do? So we need to take the wave function, so the vacuum wave function. Let's think of the vacuum wave function as a wave functional of the field values on the left and the field values on the right. Okay? So let's say we have a scalar field for the sake of the argument. We could have many scalar fields and many other types of fields. But for the sake of the argument, we say that it depends on some variables that are localized on the left and some variables on the right. Now we could get this function. So here we have some. So phi left of x is some arbitrary function, which is the argument of the wave functional. And phi right is again some arbitrary function here defined on the right, which is again an argument of the wave function. Okay, the wave functional. So we can get this by doing evolution in Euclidean time, right? So we can get the vacuum wave function by evolving from an arbitrary state in Euclidean time up to Euclidean time equal to 0, right? And that will prepare for us an unnormalized wave functional, right? So we can do that. So then we also need, so that gives us, let's say, the ket. Now we need the bra. So the bra is the same thing. And we'll write it on this blackboard. So we get the ket we get by doing Euclidean evolution. So now this is filled by Euclidean evolution up to Euclidean time equal to 0. And on the top we have the same thing, Euclidean evolution up to time equal to 0. I'm just separating these two for visualization, but they're on top of each other. And now we are instructed to trace over h left. So we are instructed to set the function. So we have here some functional phi right on the bottom. We have some different function phi right on the top. But the functions here on the left are the same on the top and bottom because we are going to trace. And we are going to integrate over all possible functions. Right? Now doing this is like doing the full functional integral, not inserting anything here. So now we have the functional integral over all of Minkowski's, all of Euclidean space with arbitrary boundary conditions on the bottom of this slit and the top of this slit. Okay. So that's the thing that is computing for us the density matrix rho r, right? You can think of, so normally a density matrix is the density matrix that depends on two indices, alpha and beta. And you can think of the index alpha as being this function and the index beta as being this function. Okay. Yeah.
So when you write the ground state as being a function of the left and right
yeah.
fields, do you have like left and right ground states that those fields are acting on, or?
No. Well, the ground state is the. Let me see. You should think of this as just real functions. Okay, just they are not operators; they are functions. Right. So we're not discussing yet operators which act on some states. So we are taking, let's say, the Schrödinger picture. Okay. Yeah. So then just to clarify that, so an operator here would be a function of this function. Okay. Yeah.
Are these kind of left movers and right movers?
No. They are. This is the function. This is the field itself, and it's the value. So it's the value of the field at this time, at t equal to 0. And then in a quantum field theory, we would average this value of the field with some function. So for example, in free field theory, we would have the ground state wave function would be a Gaussian function of this field, which is not a local function of this field. It's a non-local function. So, yeah. So more precisely what we do in order to find this function is we divide this in Fourier modes, and then for each Fourier mode, we have a Gaussian wave function. And then the fact that we did this Fourier transformation tells you it's a non-local expression. Yeah.
Could you go over the Euclidean evolution and why that compares back?
Yeah, so this is something completely general in any system. If you have any state psi and you evolve in Euclidean time, right, you'll get the minimum energy state, which by assumption is the vacuum, by the definition. The minimal energy state, you evolve for a long time, you project onto that state. So it's a way of preparing the vacuum. So that's what gives us this density matrix. But now notice that you can think of this as evolving in the angle. So if we think about Euclidean evolution in the angle, so we take a time which is this angle, the Euclidean time which is this angle. We're evolving by length 2 pi, right? The whole situation is rotational invariant. I mean, the dynamics of the theory, if you wish, is rotational invariant. That comes from the Lorentz invariant of the original theory, invariance of the original theory. So the Lorentzian theory, which is Lorentz invariant, leads to an analytic continuation to Euclidean time, which is rotational invariant. And we now have that this quantity then can be expressed as an inner product of the function psi right of the operator e to the minus 2 pi b. B is the boost generator is the same as this rotation generator, Euclidean signature. The 2 pi comes from the 2 pi angle, and then we have the function phi right, phi left and phi right here. So I use these functions to specify, but we can, the operator expression is this, and then we can evaluate this operator in any basis that we choose to do so. Okay, good. So that's that's a very important property of quantum field theory, of relativistic quantum field theory. Notice that it depended crucially on relativity. And this is related to the so-called Unruh effect. So far I've given a somewhat abstract discussion of this. But imagine that you are an observer who follows this accelerated trajectory. So to be a little more precise, imagine we choose a metric which is minus. This is a way of parametrizing this two-dimensional Minkowski space by some coordinates where fixed r corresponds to one of these hyperbolas, and tau there is time along here. So more explicitly, we could say that x plus minus is plus minus r e to the plus minus tau. Okay? So if you're an observer at fixed r in those coordinates, in the original coordinates, you look like an accelerated observer, which has constant proper acceleration. Okay? The proper acceleration you feel depends on exactly where you're sitting, and that constant, let's say this is the proper acceleration, is equal to 1 over r. Okay? So if you are at r very close to 0, you really feel a very strong acceleration. If you are at larger values of r, you feel a weaker acceleration. So this person sees a constant gravitational field, very much similar to the one we feel here, standing at the surface of the Earth. And then this person will see a temperature which, recall that here in these coordinates, the boost generator is just simply derivative with respect to tau, right? So it's just the boost generator is just the energy. This is sometimes called the Rindler energy. So it's the these coordinates are sometimes called. These are all names. Maybe I'm just saying it if you've just seen them before, but it's not very important. And this is the energy measured with respect to this time, right? And so then the temperature associated to this energy, again, measured relative to this energy, is 1 over 2 pi. So that just comes from the calculation we did before. I'm just noticing that B is the same as this energy. And then from the expression of the density matrix, we read off the temperature, which is 1 over 2 pi. Okay? This is the derivation that this observer will see this temperature, right? So he's seeing a density matrix for all his observations, which has the thermal form. So any of his observations will be described in this way. Notice this is, if you wish, some coordinate temperature. So temperature measured with respect to the energy, which is conjugate to this time. The proper temperature that he will measure will be 1 over 2 pi So that the original one rescaled by the redshift factor here. And that redshift factor is 1 over r. So it's really 1 over 2 pi times the acceleration. Okay. So an accelerating observer sees a temperature equal to the acceleration. So all of this is in units where h bar and c are equal to 1, and you can go and put in the factors of h bar and c. Now, one very important point to make here is that this is actually a non-local effect. So if you only have a portion of this space-time, so if you only, well, before let me make a positive thing. By non-local, what I mean is the following. So the proper temperature for an observer sitting at some distance r from the origin goes like 1 over r. So this means that the wavelengths, the thermal wavelengths of, let's say, photons or massless particles emitted by present in this thermal bath will be of the order of 1 over the temperature, which in this context will be of order r. Okay? So the typical wavelengths associated to this effect are of the same order as the distance to the horizon. Right? So in other words, this effect is sensitive to the structure of the host, depends on the structure of the host time all the way to the horizon. Okay? Yeah.
Can I say that if I start from a pure state and then I look at it in an accelerated
Yes.
reference, then
Yes.
I get no longer a pure state?
Yes. I should have emphasized that. So we started with a pure state, and we are accelerating. We get a mixed state. It's a mixed state that is mixed, but in addition, it is thermal. It is just simpler than a generic mixed state. But yes. And the reason you get a mixed state is that you are not able to, if you are accelerating, you are not able to measure anything that is here. So you are accelerating, you can get signals, let's say, from here and so on, but you can never get any information about what's going on this side. So you have a big system and you are restricting what you're looking at. So this is generic in all these problems in quantum mechanics. If you only look at one portion of the system, a pure state can look mixed. So that's what. Okay, so that's that story. So now let me just to clarify what the point I just made. Let me notice that now on the surface of the Earth we are in an accelerating. We are feeling some acceleration, which is the acceleration of gravity, g, 10 meters over second squared. Okay. And as an exercise in h bars and c's and so on, actually only c's, we can calculate the thermal wavelength so this acceleration we feel, which is due to gravitational fields, will also be felt by someone who's accelerating, right? In ordinary Minkowski space, if he's accelerating with this acceleration, this proper acceleration, he will feel exactly the same as we locally feel, okay? But we just said that if this person is accelerated in Minkowski space, he would see a temperature, right? Instead of calculating the temperature, let's calculate the associated wavelength. And you can work it out from here by putting it the correct factor of c, the factor of c squared. And it turns out to be 1 light year. Okay. Now, is this a measurable temperature? Well, this is a very low temperature, right? Now, does this mean that if we are here on Earth, and of course our temperature on Earth is much higher than this, but let's imagine we cool the Earth to absolute zero, okay? So we imagine that we are in the surface of a planet that has cooled completely to absolute zero and so on. Will that person in the surface of that planet see a temperature? How many people think that? Let's do a poll. So how many people think that he will see zero temperature, and how many people think that they will see a temperature, which is the inverse of 1 light year? Okay, no take is for any. I guess you're not supposed to abstain. So the answer is that the derivation of the temperature depended on having Minkowski space all the way to the horizon. Okay. So if you have Minkowski, if you have something that looks like this Rindler space, but only in a portion very close to the trajectory, right? Then you might or might not have this temperature, right? So for example, if you had a mirror here, and you don't even have the left side, then you might have a state. I mean, you could certainly have this thermal state, or you could have a state which has a different temperature, including 0 temperature. In particular, in the case of the Earth definitely, the gravitational field in the Earth does not look like Rindler space to distances which are of order 1 light year, right? So when you go to 6,000 kilometers, you have slightly different shape for the gravitational field and so on. And if you think of r as some radial coordinate, it is as if space ended here, and you have a different geometry. And that different geometry is such that you can actually have any temperature you want, including 0 temperature. Okay? So this is emphasizing the fact that in order to actually see this, to really derive this Unruh effect, you really need to have Minkowski space all the way to the horizon. You need the presence of this horizon. Okay? If the horizon is not there, then you are not forced to have this temperature. So it depends on the presence of the horizon and the fact that there is nothing special happening at the horizon. You have smooth fields at the horizon. Okay. One can be a little more explicit in. So was this point clear or not? Yeah. One can be a little more explicit by in the description of this state. So one can, for example, decompose the fields here in the right Rindler wedge by using modes which have definite frequency under this time translation. So let's call them, you would need to solve the field equation in these coordinates, and you solve for modes which have frequencies which are e to the plus minus time, and then some function omega of r, which depends on the mass of the field and stuff like that. But then, so to one of them, you associate creation operators, and to the other, annihilation operators, so b omega and b omega dagger. And there will be one for the left modes and one for right modes. Okay. So there is a whole set of these, b omega right and b dagger omega left. And so you can define a certain Rindler vacuum, which is annihilated by all these annihilation operators. And then what happens is that the Minkowski vacuum will look like look like this in terms of this Rindler left and right creation operators. So this is a slightly more explicit. This is one explicit form of writing the original vacuum, 0 Rindler, 0 Rindler left. So this is the Rindler vacuum left and right, and this is the Minkowski vacuum. So so here we are trying to write this artificial vacuum where you have the vacuum left and right and it's factorized, and then all these creation operators are creating an entangled state. Right? Each time we bring down one of these exponents, so let's consider. So we'll have a state which is 1, then we have e to the minus omega beta over 2 b omega dagger b for the left and the right creation mode, and so on, right? So this is creating an entangled state, right? So we have state no particle on the left and right, and then one particle on the right, one particle on the left. So this is a description. This is not really, this is a Rindler, let's say, particle or mode. This type of descriptions are not strictly correct because of ultraviolet divergences. So the fact that the Hilbert space cannot be quite split into two parts, but for many practical purposes, this description is okay. And this is true entanglement, and it can be used to generate violations of Bell inequalities, right? So as true entanglement can always be used. So there you set up a situation where you measure some field operators here, some field operators here, and you can do non-commuting measurements and so on in such a way as to violate the Bell's inequalities. Okay, so this is interesting, but well, is it ever relevant for us? So is this effect relevant for anything? Okay, and so we saw that, for example, regular acceleration is very, very tiny to create any interesting measurable effect. But I would like to argue that actually this effect is hugely relevant in the cosmological setting, because in the early universe we had a period of inflation where we had a universe which was expanding with constant acceleration, where the acceleration is equal to the Hubble constant, which had a very large value, 10 to the minus 5 times smaller than the Planck scale. And then an effect which is a very close relative of this, or essentially the same as this, because in an inflating universe, you also see a horizon. You see this cosmological horizon. And if you expand the fields near the cosmological horizon, you have a problem which is essentially identical to this one. And again, you have a temperature which is equal to this acceleration, up perhaps to these factors of 2 pi. This temperature created fluctuations or inhomogeneities in the early universe that then grew to where the seeds for cosmic structure. So in the beginning, the universe was very, very uniform with little tiny perturbations, which were created by this effect. These perturbations of order 10 to the minus 5, which then grew to become galaxies and so on. So it's not just purely academic interest, but we actually use it for understanding aspects of nature. Of course, this is just a theory of the early universe, but it's the best theory we have. Okay, so that's just a selling point for this effect. Now, let's discuss some more formal. Yeah.
The effect creates fluctuations. So is there like local inhomogeneity with the acceleration?
Yeah. So it's a temperature, and whenever you have temperature, you have thermal fluctuations, and so the universe was not exactly uniform, but had small. Well, to explain all the details would take me longer. But let me say that during inflation there was a certain clock, right? And that clock is a field that is moving in this space. It's evolving in this space. And that clock, the field is a model for this clock, but whatever the clock was, the point is that it had these quantum fluctuations, sometimes people describe them as quantum fluctations, but of course this temperature has an h bar in it. So it's a quantum effect. Has an h bar here in the. So you take h bar to 0, it disappears. And but well, these fluctuations in the clock make the universe expand a little more in some regions than in others, and that created initial inhomogeneities in let's say a spatial surface of the universe. Okay, so now, other questions? Okay, so now I'd like to discuss some other aspects of this. And one other aspect is the computation of the entropy of these density matrices in quantum field theory. So we take that density matrix we discussed, and we could calculate its entropy. The entropy. So calculation of the detailed calculation depends on the system we have. Now, notice that I've talked about two-dimensional Minkowski space, but this is true in any number of dimensions. If we can add here a certain number of transverse dimensions, and the whole discussion goes through without any single change. Okay. A funny thing about the Unruhe effect is that Unruhe in German means agitation. And so it's one of these examples where the physicist's name is related to the effect they discovered. Anyway, so that's a funny curiosity. Well, entropy. So one way to estimate the entropy is to say that, well, very close to r equal to 0, we have very high temperature. And so we can neglect the masses of the fields if we had massive fields. And so we can think of the entropy as an integral over the transverse dimensions and of some entropy density. And this entropy density, by scaling symmetry, the same argument I given you last time, would go like 1 over r to the d minus 1. Okay. And so this whole effect will go like the area divided by, we integrate, it's divergent, and we have to put the short distance cutoff at small r, and we'll go like the transverse area to the power d minus 2. So d is the dimensional space. For example, in a four-dimensional theory, this would go like, the transverse is really an actual area divided by epsilon squared. Okay. Okay, so that's ultraviolet divergent. Now, this is this fact. So this ultraviolet divergence is actually the same for any region. So if you take here, we took a region which is really half of space. So if we have even more dimensions, we are dividing the spatial surface into two pieces. The spatial, take the surface at constant time, we divide it into two regions. But if we were to take any other surface of any other shape and divide space into region A to be this shape and then something else, we will get the same type of ultraviolet divergence. And the argument is simply that since this depends on the short distance structure of the theory, locally near any small patch of the surface, we have a story which is similar to the one we were already discussing. Okay, so that's true in any relativistic theory, and actually in any state in a relativistic theory, it is true that the ultraviolet divergent part goes like the area. Now, finite pieces might or might not go like the area. I mean, for example, if you have a very complex pure state, for example, a constant energy density state that is, let's say, was initially pure and it's now it's kind of thermalized, self-thermalized, then the entropy density here, the entanglement entropy here will go like, we'll have a finite piece going like the volume of the region, right? Just as ordinary thermal entropy does. Okay. Now there are many, in quantum field theory, and I'll discuss some of those aspects later, there are many interesting things you can say about finite terms that come in here. So as many things which are divergent in quantum field theory, this is divergent, and the divergences are fairly universal. And there are here some subleading divergences which are also universal. And then there are finite pieces which are many times interesting. And I'll perhaps postpone the discussion of those to later. So now I'd like to go back to black holes. So the application of this to black holes. So if you take a collapsing black hole, for example, in flat space, then we can draw a causal diagram or Penrose diagram for this collapse, which roughly has the following form. So these causal diagrams correspond to taking the original metric of the spacetime and then rescaling the overall factor of the metric by a function which doesn't affect the causal structure, so the direction along which lines are projected. So it's a kind of projection of the infinite, let's say, space into finite region, a little map of the geometry that highlights its causal structure. So here we have a star, let's say, that collapses, and the asymptotic region, so the whole region far away Minkowski space, is here. And so a point that is in this region of space-time can never send a signal to someone who is completely outside. So that's the diagram for a collapsing black hole. It is sometimes useful to consider the solutions of vacuum Einstein equations, which are rotationally symmetric, and the solution of that kind is a so-called extended Schwarzschild black hole. Has two asymptotic regions. We'll discuss its interpretation a bit later. But the point is that this region of the geometry is actually very similar. So it's essentially the same as the late time region for a black hole. So in some sense, when a black hole collapses, it settles to a geometry which is essentially the same as this one. And when you look at this geometry, it has this region here, which looks very similar to two-dimensional Minkowski space. Unfortunately, I erased the diagram of two-dimensional Minkowski space. But it also looks similar. And now if you're an observer who sits outside, you see that you are analogous to those accelerating observers in Minkowski space, because you will only receive signals from this region. Okay? You will never receive signals from this side or what is here in the interior. Okay? And in fact, this temperature that a local Minkowski observer here will see translates in the temperature that someone who sits far away from the black hole will also see. Okay? So that is the same as Hawking's effect. So this Unruh effect near the horizon translates into the Hawking effect far away, the fact that the black hole emits thermal radiation. Yeah.
So what represents the wiggle line?
What's the wiggle line? Ah, sorry. Yeah, this is the singularity. And this line here is the horizon. And this whole region here is what we can call the exterior of the black hole. So black hole has a geometry which has the following features. So if you are an observer, you are following a time-like trajectory here, right? You cross the horizon. Once you cross the horizon, you can never come back out. But the horizon is not a bad surface. I mean, you don't feel anything special when you cross the horizon. It's like any other point in your space-time. But once you cross the horizon, you cannot come back out, and furthermore, you will end up in a region where the gravitational forces are so bad that you will die. Okay.
What are the straight lines?
The straight lines? Yeah, so this is the r equal to 0, the origin of, yeah. So let me first draw the same diagram for Minkowski space, right? So I'm going to draw here the radial direction and also the time dimension, and they've been rescaled so that we can fit them in this diagram. And on each point here, there is an S2. There is some two-dimensional sphere, which is very big far away, and as we go to the center, it shrinks to 0 in a smooth way at r equal to 0. Okay? And so this is essentially the same diagram. And here also the two-sphere is shrinking, and that's creating, but not in a smooth way. It shrinks in a way that creates a curvature singularity, a region where the curvature goes to infinity and tidal forces go to infinity. Okay. Now, if we have a quantum field on this geometry, and we restrict to observations done outside, we'll also get an entropy. So that entanglement entropy we were discussing before, we'll also have it. So we'll have this is for the quantum field theory in a black hole background. We'll also have this term that will involve the area, let's say in 4 dimensions over epsilon squared. But the black hole has also a bigger gravitational contribution to the entropy, which is the area over 4L Planck squared. And here the coefficient of this term in the quantum field theory is somewhat ambiguous because it depends on exactly how you do the cutoff, whether you do it at epsilon or 2 epsilon and so on. Here the coefficient of this term is completely fixed. It's and it's calculated not by summing over some Hilbert space, but it's calculated using the Euclidean gravity action, for example, as we discussed last time. Right? So now, in general, the Planck scale is in a gravitational system is supposed to be the shortest distance you can consider. And so, if you have a quantum field theory, it's unreasonable to choose the cutoff of the quantum field theory shorter than the Planck scale. So, always this contribution will be somewhat smaller than this contribution. But it's a contribution that seems to that is there. And one way to understand it is to think that well, this is L Planck, of course, is just G Newton. But one way to think about this is that we first calculate this with a bare G Newton, where we don't include any quantum effect whatsoever. And then we calculate the quantum field theory contribution, which will give a 1 over epsilon squared, plus perhaps something finite. And then this whole thing turns out to be the renormalized Newton constant. Okay? So you can independently try to understand how the Newton constant renormalizes, and in some situations this is the correct renormalized Newton constant. And in situations where it doesn't happen, well, let's say morally this is the renormalized Newton constant. So in some sense, the black hole entropy knows about this divergence of the entanglement entropy and gives a kind of regularization of it in a way which is a bit mysterious because the black hole entropy was not computed by tracing over some microscopic Hilbert space, but was computed by looking at the gravity solution. And if you look at how the Euclidean calculation works out, it really amounts to the following statement. So, how do you compute entropy in a theory? So you take your system and you take the partition function and you vary with respect to the temperature, right? Keeping everything else fixed, you vary with respect to the temperature, and that way you calculate the entropy. You have to calculate the first derivative with respect to the temperature. But what happens in gravity is that if you have a black hole and you vary with respect to the temperature, you make a variation of the temperature, then you also vary the geometry here near the horizon in such a way that the Unruh temperature matches the temperature you are putting it from the outside. Okay? So the way it regularizes is by always matching the temperature to be equal to the acceleration. Okay? So somehow we cannot, in this gravitational context with dynamical gravity, we cannot change the temperature to be different than the local value of the acceleration, at least when we are very close to the horizon. Far away it can be different, but when you get very close to the horizon, it's actually equal. So one way to say this is that, Aristotle said that nature abhors the vacuum, and we can say that gravity loves the vacuum. So it wants to have the vacuum near the horizon. Yes?
Regarding those two statements, a clarification. So the QFT calculation is considering quantum fields on the background space-time.
Exactly, yes.
And the gravitation, I don't quite get it. So it's purely classical gravity calculation?
Yeah, it's a classical gravity computation. So So let me describe the gravity computation of that entropy. So one way to compute it would be to compute the black hole mass, okay, and then from the mass find the temperature, right, which will depend on the mass, and then use that dm is equal to t ds, right. And in this way, find ds. and then you integrate from m equal to 0 to m, and in this way you find the entropy, and it turns out to be equal to the area of the horizon. This is one simple way to describe it. So another way of calculating is, which ends up being the same, gives the same answer, is to consider the Euclidean black hole, which has a thermal circle far away, so it has a Euclidean geometry, which contains a circle. And then, for a given length of this circle, you have to choose the black hole mass in such a way that here you have a smooth, the circle shrinks smoothly at the position of the what would be the horizon in the Lorentzian theory, but in Euclidean theory it's just like the origin of space, very similar to what was happening in two-dimensional Minkowski space. And then you calculate the gravitational action of this, which depends on the temperature. That's a simple gravity computation evaluating the Einstein action. And then you apply, the usual formula, beta d beta minus 1 of this, and then that's the entropy. So notice in this calculation we never talked about sum over states, right? So it's if you wish, a macroscopic calculation of the entropy. So this approach, for example, would be what an experimentalist in the lab would do to calculate the entropy of some material. Would take it at 0 temperature, and then you integrate the little exchange of heat until you get the total entropy.
How is the Planck length scale from this picture?
The Planck scale here appears because the temperature is related to a geometric property of the black hole, the size, right? And the mass is related to the size by a factor of g Newton, right? So in the formula for the metric of the black hole, we have something like g Newton times the mass divided by r, right? This is what I was calling the geometric property, the Schwarzschild radius. Maybe there's a factor of 2 here, I don't remember. But the point, this is where g Newton is appearing. Right? So when we relate the mass to the temperature, there is a 1 over g Newton here, and that's where it's going to come in. So it appears, that there are no sum over states or anything. And so it's always, so the question is, the question you can ask is, well, where, how can I give this entropy, this gravitational entropy, a statistical explanation, right? Can I give to it a statistical explanation? And the statistical explanations we have, some of them they typically go through something which is morally similar to this gauge-gravity duality, where you say, you have the black hole, I see it from far away. There is some alternative, let's say, dual theory, where the black hole looks like a thermal gas, and then I compute the thermal gas in that dual picture, the entropy of the thermal gas in the dual picture, and that matches the black hole entropy. So that's typically what you do.
Yeah, I think it's related to his question. I still don't get how do you get that 1 over epsilon squared contribution in S gravity?
This is a quantum field theory computation, right? And we got it from the high temperature near the horizon. Okay.
Oh, so
this one here.
Yes. So there you sum over states.
Yeah. Here, this piece has a statistical explanation, but this piece is in some sense always a sub-leading correction, because this is to leading order in 1 over the g Newton expansion. This is the next order, and so the well-defined way to do this computation is first to calculate work at very small values of g Newton. This is the leading contribution, and then this is a sub-leading contribution, which could be divergent, but we absorb the divergences in the leading contribution. We are always going to take epsilon to be larger than L Planck, right? So in this approximation, we never have epsilon smaller than L Planck. So this is never bigger than this.
So we want a statistical interpretation for the leading contribution.
Yeah, we want a statistical interpretation for the leading contribution, and the point I'm trying to make now is that there is a sub-leading contribution to the leading one, which looks very similar to the leading one, which does have a statistical explanation. So in some sense, it looks as if the gravity is regulating this UV divergence in some way which is universal and depends only on the Newton constant. But we don't know how to give a direct bulk interpretation of how this regularization works, except to say that the way it works in detail is that you change the background in which you're doing the computation, and that's yeah.
And maybe I just missed a bit. You said the Unruh picture near the horizon matches onto the Hawking picture.
Yeah. So the Unruh picture near the horizon implies the Hawking radiation.
So what do we say for somebody at like an intermediate R?
Well, what we say is the following. So I said before that so we have r squared dt squared plus this was the metric of Minkowski space, right? And in this situation we had this temperature which was 1/2 pi, right? So the metric of the black hole is a little more complicated. So there is a Schwarzschild radius dt squared plus dr squared 1 minus r Schwarzschild over r. I don't know. I'm just giving it for completeness, but so it's something like this. It's a little more complicated, but near r equal to rs, we can do an expansion of this metric that looks exactly like this with a slightly different coefficient here in front, right? And so that temperature, which was 1/2 pi in these tau coordinates, in these t coordinates, and that ends up being a temperature which is 1/2 pi, 1/rs, and maybe some extra factor that comes in put in the metric. I think it's maybe a 4 pi. I don't remember exactly. But you can do it as an exercise to match first this metric. And so that's what we get. And recall that we said yesterday that if we have a gravitational system which has a time translation isometry, right, and it's at thermal equilibrium, then the temperature relative to this time is always a constant. Right? So we can have a situation where we have a thermal gas outside the black hole. If it is at this temperature, it will be in equilibrium with the black hole. And in general, if we form a black hole, it will not be in equilibrium. There will not be any particles falling in, right? So if the outside is at lower temperature than the black hole, there will not be particles falling in, and there will be more stuff coming out of the black hole. In a black hole that actually forms in nature, there will be more particles coming in because the CMB temperature is actually bigger than the black hole temperature.
But physically, what we would say is that you have somebody on the outside, and they would just be seeing some sort of particles and measuring some temperature.
Yes.
Would you describe that as a Hawking or Unruh temperature? It's irrelevant.
Well, strictly speaking, the Unruh effect is supposed to be the one where you are very close to where it's locally Minkowski space. So very close to the horizon is Unruh, and far away it's Hawking. This is just the definition of the names that we assign to. Yeah.
You also mentioned that near the horizon, the temperature will be in equilibrium with the gravity.
Yes.
And why is that? Why can't we have a situation like Earth where we have a temperature?
Right. So the condition that things are smooth at the horizon. So if you try to set up a condition different from the one, where the temperatures are not equal, you are creating some object near the horizon, and that object falls into the black hole, and so that's so it's just the fact that we have the vacuum near the horizon doesn't allow us to change the temperature from the acceleration temperature.
And if you have a temperature lower than the Unruh temperature?
Yeah, imagine that you try to make the temperature lower. Immediately the black hole emits radiation and it brings it up to the right temperature. And that process, you would call it as the thermalization of the equilibrium condition for the black hole. Now there is some discussion of whether this the black holes, this description I'm telling you right now, what the black hole is doing, is actually correct for very long times after the black hole forms. So Hawking's initial argument is strictly valid as he originally wrote for some time after the black hole forms, the time which is r Schwarzschild times the log of r Schwarzschild divided by r Planck. That's which is a relatively short time, but I think there are good arguments that this description exists for a long time. But you tend to run into some paradoxes if you try to. Okay, let me discuss a little bit about the information paradox. So in the case of quantum field theory, right? So if we take the right side of the quantum field theory, we find the thermal density matrix. And we know what's purifying that density matrix is this left side, right? And if we have both the left and right side, then we have an ordinary, we have a pure state. Right? Now, if we look at the black hole and we look it from the outside, it looks like a thermal system, right? So some system at a finite temperature. And if we think that the black hole entropy should be interpreted as the log of the dimension of the effective Hilbert space where the black hole lives, right? So the black hole has a finite number of microstates characterized by whose number is the dimension of this Hilbert space describing the black hole. Even if we don't know exactly what it is, if we think that this is what the entropy is measuring, and this is everything that can interact with the outside, then from the outside it looks like, well, we have some system with a finite number of degrees of freedom, which in principle could be derived by could be described by some unitary theory. So in that description, the fact that the black hole is thermal would be an approximation, but if you form the black hole with a state you know, you would, in principle, be able to calculate what comes out. Right? And in AdS CFT situations, if you assume the gauge gravity duality as being correct, then you have an explicit description of this Hilbert space. It's the Hilbert space of the boundary theory, and in principle, you can calculate what comes out. Okay. On the other hand, so then you can ask the following question. So imagine that you have the black hole, and I entangle this black hole with some other system I control, right? So a thermal system can be then entangled with something else. So imagine that I entangle this black hole with a set of spins. So we have some spins out here, and we let this black hole exist for a long time, and we entangle it with the spin in such a way that it's maximally entangled with the spins. Then we have this funny situation, because on one hand we would like the black hole to have a smooth horizon, right? So we have a mode here which is supposed to be entangled with some other mode that is moving here to the right. On the other hand, this mode was contributing to the black hole entropy, and therefore this mode then would be entangled with the set of spins, right? But on the other hand, it has to also be entangled with this guy who is inside, right? And this seems impossible, so it would violate the strong subadditivity condition and so on. So you cannot have a spin that is maximally entangled with two different degrees of freedom. Okay. And so this leads to some paradoxes that have led to some people to say that a black hole which is maximally entangled in this fashion will not have a smooth horizon. Okay. I think this conclusion is wrong. But before I go to that, let me discuss a little more the so-called eternal black hole. So we have, so we can take this geometry, which is the simplest spherically symmetric solution of vacuum Einstein equations. And that geometry has a diagram which, well, that geometry, first of all, those coordinates describe this portion of the full geometry. But we can go behind the horizon and extend these coordinates behind the horizon. And the full extension has all these regions where we have an asymptotically Minkowski space on this side, and a second asymptotically Minkowski space on the left side, and this future interior, and then this somehow past interior. So those are the different regions. And if we were to take a time slice here through t equal to 0 slice, then that slice has a geometry which has this shape. So at each point on this diagram there is a two-sphere, and the two-sphere, so it's very large far away, and then starts shrinking, and it shrinks to some minimum value there. So here far away we have a geometry which is R3, and then that's the shape of this slice here. And then the spheres shrink, and they shrink to some minimal size here, which is the size of the horizon. And then on the second side, they start expanding again and forming a second separate R3 region. Okay. So this peculiar feature of this simplest solution of Einstein's equations was noted by Einstein and Rosen in 1935. And for that reason, this is sometimes called the Einstein-Rosen Bridge. I mean, it's curious that they noticed the existence of this geometry even before they understood that the horizon was non-singular. So in their paper, they apologize for going through this singularity at the origin and so on. Okay. Now, so one question is, what's the interpretation? What's a possible interpretation of this geometry? What's going on with that geometry? I should say that whenever you have a collapsing black hole that collapses from matter, from some non-singular initial conditions, you do not get that geometry. You get only a portion of this geometry. I think unfortunately I erased the diagram for the collapsing black hole, but we discussed it in some detail a moment ago, and it only coincides with that geometry in this region, right? But not here where we have the matter, where the equations are different. But nevertheless, we can still ask whether there is any interesting interpretation of that object. And this type of geometry is very common. It's also common when you consider a black hole in anti-de Sitter space. There, the diagram is just slightly different. Instead of being asymptotically Minkowski space, it's asymptotically de Sitter. So here we anti-de Sitter. So here we have the boundary, the same boundary we were discussing in anti-de Sitter space. So imagine we have a CFT on SD minus 1 times time. And so here I'm only drawing the time dimension and the extra, let's say, holographic or extra dimension that we get in AdS CFT. So that's the Lorentzian solution. The Euclidean solution can be drawn as follows. So we have the Euclidean time circle we discussed several times of length beta. And this circle in the interior shrinks completely and in a smooth way. So this point here in the center corresponds to this point here. And in fact, this slice of the geometry corresponds to this particular slice of this Euclidean geometry. Okay. So you can view the bottom half of this geometry as a way to prepare the initial conditions for the Lorentzian theory. So let's say a way to prepare the wave function of the system at t equal to 0. So I mentioned before that sometimes you can view Euclidean evolution as preparing you the ground state. So here we're not evolving over an infinite amount of Euclidean time. We are doing this funny evolution over Euclidean time in an interval. And when you do that, you create a state which is an entangled state. So first of all, when you cut at t equal to 0, so from the boundary point of view, we are having just an interval in Euclidean time. And we have two Hilbert spaces, the Hilbert space of the left side and the right side. These are two separate field theories that do not talk to each other. So evolution over an interval will give us a wave functional which lives in the Hilbert space of the left CFT, tensor the Hilbert space of the right CFT. And the state, you can say exactly what it is. It is simply, well, the state is proportional to normalization constant to the sum over all possible states of the field theory on the left of e to the minus beta En over 2 times En for the left theory and En for the right theory. So that's the form for the state that we get, and this is totally general. This is whenever we evolve a Euclidean theory over a time of length beta over 2. Okay, we produce this state. Okay, this is just simply that we are summing over all states, and the evolution over beta over 2 is giving us this Euclidean factor. The important fact about this state is that it's a state that is an entangled state in the two CFTs. And we can compute the entanglement entropy, and not only the entanglement entropy, but the full density matrix of a subsystem. So the full density matrix of the right subsystem is just e to the minus beta h of the right subsystem. Okay. So when we take psi and psi conjugate and we sum, we get two factors of e to the minus beta e over 2. We get this factor. And in fact, yeah.
So this might be a silly question, but I was thinking that this solution to Einstein's equation, this is any general spherically symmetric solution.
This is the only spherically symmetric solution, vacuum solution. Yeah.
Yes. So does it really care that we have a black hole or not?
Well, you mean this one?
No, that one.
No, this one.
Yes.
Well, this one is the black hole metric, right? From the outside, it looks like a black hole. So it has two outsides, and each outside looks like a black hole, and they are connected through the middle. It's like you have two separate universes connected through two separate universes with a black hole in the center, and they are connected through the middle, through this black hole.
So if you didn't have matter at all?
Yeah, this solution has no black hole. Yeah, no, well, it depends on what you do. So you could imagine not having matter at all.
Yes.
You start with Minkowski vacuum, with the Minkowski space, and you send gravity waves, right? If you do that, then you'll create a certain black hole, which would not look like this one. So this is not something you can create by sending stuff from Minkowski space. So you'll create something which, well, will be more complicated, but it will be morally similar to this guy. Okay. We're trying to discuss what we should do with this. I'm going to get to that. Well, I'm running out of time. What time am I supposed to stop? I think I started late, right? Yeah, 10 more minutes. Yeah. Okay, so this little. So I said this little trick for constructing the thermal density matrix of saying instead of having a thermal density matrix, we double the system. And we now have a pure state on the double system. It's a generic trick people sometimes do for various purposes. And this state is sometimes called the thermofield double. So you double the fields, and then if you take that thermofield double state and you consider only operators that act on the right? So this could be different operators, but all the operators act on the right. Then there is no action on the states on the left. You can somehow sum them over. And this is the same as trace over just the right side of this row right and the same insertion of operators. Okay. And thinking about it this way might be useful for some purposes. I won't discuss which purposes. But so what we are learning from these diagrams is that these eternal black holes, this type of maximally extended black holes, could be viewed as the geometry associated to this thermofield double construction. So we are constructing a state that we get here at t equal to 0. And at t equal to 0, then we could go to the now Lorentzian evolution. And Lorentzian evolution would produce for us this upper half of the black hole. So we can think of this geometry as describing this particular entangled state in the quantum field theory. And you can check this makes sense. So for example, you can compute the correlation function of now an operator on the left and an operator on the right. And you find some results which are in agreement with this idea. Now, this geometry has an important property, which is the fact that you cannot send signals from the left side to the right side. So if you attempt to send a signal from, let's say, the right side, it will always end up at the singularity, but it will never reach the left side. Okay? That's related to the fact that all operators on the right commute with all operators on the left. So you cannot really send a signal. And the fact that, and this is consistent with the idea that this geometry should be interpreted as an entangled state, because if you have an entangled state and you do anything on one subsystem, you cannot send a signal to the second subsystem. So you cannot send signals through entanglement. Now, it's amusing that the fact that you cannot send a signal in this type of geometries is quite a non-trivial statement in GR. So it depends on the null energy condition. So the fact that when you take the, let's say, plus components or null components of the stress tensor, you always get something positive. And so with this assumption, you can prove that no matter what you do, what kind of precise setup you have, you can add Maxwell fields, you can add matter, you can add whatever you want. The geometry gets deformed and so on, but you can never send a signal to the other side. Okay. It is even more fun quantum mechanically, because quantum mechanically you can have that this is negative in some regions. But actually, if you integrate over a null line, t++ is actually always positive. If the null line is, if again you cannot send signals from one point on the null line to the next point on the null line. So, so this is something that hasn't been totally proven under most general circumstances, but it's general believed to be true that if you take a null line, this will be positive. I mean, it's been proven under certain assumptions, but not in the most general situation. But so this non-trivial property ensures that this type of you can never send signals through these geometries. And so something interesting happens when you think of these two sides as actually living on the same space. So now let's consider the following situation. Let's imagine we take a geometry which at t equal to 0 basically looks the same as this one, in the sense that we take these two exteriors and we identify the interior in the same way that is identified in this geometry. And we take these two to be far away so that they don't influence each other very much. So we can superimpose them. So that's some good initial condition at t equal to 0. And now we can evolve using the equations of general relativity for later times. And in the neighborhood of each, in the neighborhood of each of these objects, this will look like a black hole. This also looks like a black hole. And the neighborhood of this geometry actually looks identical to some region near r equal to 0 of this geometry, or some region near the horizon of this geometry. So in this situation, you have something that looks like a wormhole. You can have these two objects separated by, a long distance, so 1 light year. But you can have an object which is sitting 1 meter from this horizon, an object which is sitting at 1 meter from this horizon. Their distance is 1 light year through the outside, but the distance through the inside is just 2 meters. Okay. So you can have this. This is a solution in general relativity, and you might wonder. You can ask whether we can really go from one side to the other, right? And what we've been discussing is that we can really not go from one side to the other. So if you try to, you are here at 1 meter, and you try to go to the other side, you go in, but the sphere starts shrinking, and you end up at the singularity. So instead of going to the other side, you die inside the singularity. But there is something interesting that can happen. So imagine that that you have two people. Let's call them Romeo and Juliet. Okay. And they've been separated by 1 light year, right? They've been set one in some region, some star system that is separated by 1 light year, and they actually can. But they somehow managed to create this geometry. I'll discuss how they could manage to create this geometry. But imagine they managed to create this geometry. There is this black hole, and so the people say, well, I'm pretty sure that Romeo cannot go and visit Juliet. Okay. However, what can happen in this geometry is that both jump into their respective black holes, Romeo on one and Juliet on the other, and they meet in the interior. Okay. So this geometry has this funny feature. So even though it respects causality in the ambient space, you can really go in and they actually meet in the interior. But they cannot tell anyone about their meeting. So no one will know what happened. Okay, so that's a surprising aspect of this geometry, and maybe I think I'm out of time. Yeah. Okay.
Any questions?
Yeah. Yeah. It's a question I didn't know. Yes. Well, the Penrose diagram looks similar, but it's a bit different. So let me. So the Sitter-Penrose diagram looks like this, but this is a region like r equal to 0, so non-singular, also non-singular here, so where a sphere shrinks. And this is not a singularity, but the whole future of the Sitter space. So one difference is, so here I use the fact that on this boundary there is a field theory that lives here that I know it's well defined and so on. But in this case, we don't know whether there is a dual field theory that lives on this side. But yeah. So we don't know how to precisely extend it to the Sitter case, but maybe there is a way to. I mean, certainly the evolution in the Sitter space creates entanglement, and things are entangled. But you know, yeah. In the Sitter, you started with a single initial state, and then you produce all that we see, as Elliot was saying in his lectures. The state of the universe is unique, but we have entropy, we have all these things. And this entropy is all entanglement entropy with something else, somewhere else. Yeah.
A very naive question. So we know that according to a very rough picture that when the particles are in the gravitational field, they will be accelerated, so it looks like thermalized.
Mm-hmm.
So can I do a parallel naive analogy that when charged particle put under the electric field,
Mm-hmm.
they were also accelerated. But we never say that they look thermalized. So what's the essential difference between gravitational field and the electric field?
Well, I'm not sure. So you could consider a situation where you are in field theory with no gravity, and you have a constant electric field here, and you have a charged particle that follows this trajectory, right? This charged particle will feel temperature. I mean, if you are in a little, sphere, let's say a spaceship, right? You are sitting here, and it carries some overall charge Q, and there is an ambient electric field in your universe. You'll be accelerated, and if you do experiments there on the fields outside and so on, you'll see this temperature. It has nothing to do with gravity. So this Unruh effect has to do with acceleration and the fact that you're not seeing the whole system. Mm-hmm. So I think the answer is yes. But well, So the thing that is special in gravity is that when you produce this black hole, it automatically, the geometry itself doesn't let you see part of the system. And then it's natural to consider only the outside and the entropy of the things that are outside and so on. Yeah.
So in general, so if you have something like a null surface or something like one-way membrane, in the case of black hole, we have
Yeah.
the event horizon is like one-way membrane.
Yeah.
So we should be able to see this effect.
One-way membranes.
Like in condensed matter systems, they're trying to produce these kind of systems where.
Yeah, that's right. So in condensed matter, there's been some effort in trying to see this type of Hawking effect or Unruh effect in situations where the speed of propagation of signals might be lower than the speed of propagation of a fluid, for example. In those cases, you might see this Unruh effect, but it's different than the black hole case in the sense that in the condensed matter system situations, there is actually stuff that is going down the drain and going into some rest of the system, and you don't have an analog of the finiteness of the entropy. So in the condensed matter system, if you keep this stuff for a long time, going for a long time, you will accumulate entropy and stuff down the drain, right? While in the black hole case, you have some finite entropy proportional to the area. So that doesn't have any known analog analog I know in a condensed matter system. Well, other than the analogs through gauge gravity duality, of course. So there, you say a thermal gas, just an ordinary thermal fluid, then it has a dual description in terms of a black hole.
Okay, for the sake of time, let's ask the questions during the break. Again, we added an additional lecture at 1:30. Professor Maldacena will be giving an additional lecture at 1:30. Let's come back here at 11:10.